We have Lamas Prasad presenting in vivo measurement of gracilis muscle tendon characteristics.
Thank you for that introduction. Hello, everyone. My name is Lamas Prasad, and today I'll be sharing our work on how we measure in vivo gracilis muscle tendon parameters. Also, I'll be looking at how experimental MTU lengths compare with those predicted using musculoskeletal models. Musculoskeletal models are being used across various research fields to answer questions involving human locomotion. And in particular, they are being applied in scenarios where performing practical experiments are not feasible. To drive acceptance and broaden the impact of these models, there must be validation. The aim of this study was to measure in vivo gracilis muscle tendon parameters. This included muscle tendon unit lengths, muscle architectural data, and isometric force length data. Then these MTU lengths that were measured experimentally were compared with those predicted using OpenSim. And this highlights, or this represents the focus of this talk today, where we will look at how experimental MTU lengths compare with those predicted using OpenSim for each individual, and errors are presented as such. 4 OpenSim models were chosen, and they were scaled linearly according to subject-specific segment lengths. Data were measured from 15 subjects who were all undergoing a muscle transfer surgery. MTU force and lengths were measured intraoperatively at 4 joint configurations, shown in the table and figure here. Muscle tendon force was measured using a buccal force transducer secured to the external tendon of the gracilis, while the muscle itself was stimulated at 2 Hz and 20 Hz, and at 50% and 25% of its maximal CMAP current. And these parameters were chosen as it represented a good compromise between inducing tetany in the muscle and also controlling the large forces being produced during surgery. While the muscle was, after the muscle was harvested, it was captured using, it was recorded using photography and also weighed. Also using videos of the muscle, 3D models were created using open source photogrammetry software. While all this layouts represents or highlights the data being measured intraoperatively, as I mentioned previously, the focus today will be looking at the MTU lengths. The graph on the right summarizes experimental MTU lengths and force data, where we have MTU lengths ranging from 42 to 52.8 centimeters across joint configurations. It was observed that as the muscle lengthens, the force increases and also then decreases, where the maximum force occurred at that 3rd joint configuration or MTU length of 49 centimeters. A summary of other muscular tendon parameters are presented in this next table, where particularly to note, muscle PCSA was found to be 3 to 4 times greater than what is reported for cadaveric data, and highlights the importance of in vivo data, capturing in vivo data. Now looking at that comparison between experimental data versus model data for MTU lengths. Firstly, it was observed that models generally underestimated MTU length, especially at that 1st joint configuration, after which they then began to overestimate, where predictions got worse the longer the MTU length. A maximum individual error was recorded as 30%, and the absolute mean error across all models were between 5 and 11%. Now looking at the muscle length themselves, it was observed that this was dependent on the external tendon length used in the model, where models 1 and 3 had a much longer tendon length compared to the other 2 models and also compared to the experimental data. And as a result of this, they underestimated muscle length, particularly at joint configuration 1, where individual errors you can see exceeds 40%. Now overall, looking at all these errors, it was found that model 2 was the best performing or the best model. So in summary, in vivo gracilis muscle tendon parameters were captured intraoperatively. This included MTU lengths, where individual MTU length errors of up to 30% needs further investigation in the context